In this video, we're really going to review intermolecular forces, or really define our intermolecular forces. And in perhaps a particularly broad, sweeping stroke, recognize that intermolecular forces are really the answer to everything that we're going to see in chemistry, or biology, or even our day-to-day interactions. So really, really important stuff. But before we get there, I want to cover kind of our overview. What is chemistry? So now that we're wrapping up the semester, it's a good idea to just say, okay, what did we do? Okay, chemistry is the study of any two atoms interacting. Okay, those atoms can be connected to different things, so we're getting molecules interacting, okay, or molecules coming together, but it's really just two atoms interacting with each other. And we haven't really defined how they interact yet. But before we can get to the how, we have to address, well, what makes an atom? Okay, so we started at the very beginning of the semester saying, well, we had a nucleus, protons and neutrons and electrons, and those then defined the type of element we had. So we have carbon shown here and hydrogen. So those could now potentially interact to make bonds. And in that interaction, we could then define the types of bonds present, and we looked at them as covalent and ionic. We try to keep it big, broad brushstrokes. Okay. When we're evaluating an individual molecule, what we're then concerned about is which part of the atom is most likely to interact with another, and that ends up being our valence electron. So there's Lewis theory. Okay. How do we make bonds? That's Lewis structure. As our atoms from different molecules then interact, they can change their bonding structure and create new molecules. So we have a chemical reaction. So we could look at chemical reactions. How does a chemical reaction occur? Okay. The last part of it that we ended up going through, which was a fairly large section of our semester, was quantifying it. How do we know how many of these species are interacting? So we could look at the number of atoms present. And that was fine, at least at a superficial level, until we realized that when we move into the lab, we have no way of determining the number of the atom because they're so tiny. So then we scaled up and said, okay, I need to be able to measure things out. Well, to measure things out, I need units like grams, okay, or milliliters. Those different unit systems are going to require a new unit system to scale up the size of the atom to something that we can actually measure and work with, hence the creation of the mole. So really everything we're doing still ties back to the study of two atoms interacting. We can first look at their rough interactions based on what makes them an atom. We can then go through and quantify those interactions. That's all we've done, okay, the whole semester. How do all those things come together? But the biggest part of this that I think has yet to have been addressed is that interaction. How and why are these things interacting? What's happening at that interaction level? Well, to do that, what we can do is come up with, heaven forbid, a metaphor with relationships. We can look at the relationships between any two people. And if we take a look at these two smiley faces, they may be happy on their own, but they are now independent of each other. There is no real interaction between them. Okay? Like maybe the person you sat down next to at the very beginning of the semester, which is arguably probably not true, but we'll just make that statement. But as the semester went on, you started to interact with those around you. Okay? Probably not to this level, but maybe. Okay? Giving each other googly eyes, winks, whatever. Okay? And there now starts to build an attraction, or potentially a detraction between people, which is going to cause an opposite response. Let's look at the positive. Okay, that interaction could theoretically lead to, say, maybe dating. Okay, and now you've got these two people interacting with each other. Okay, and if that process continues to work out, we could end up with our smiley faces being married. Okay, and now theoretically equally sharing their lives with each other. So when we're looking at these relationships, we're stacking them out from being absolutely no interaction to some type of interaction to a stronger interaction to a stronger interaction. And when we look at that process, we don't go through and say, well, there's nothing to now there's something. Okay? We look at each of those stages of our relationships and we name them. We don't say, okay, well, we start completely independent and then we turn around magically, boom, married, or wedding, as I was attempting to spell, married. We don't jump from independent to married, we have intermediate stages in between it. We might have flirting, okay? And we could even add in dating. We've named these independent, or these different stages for our relationships. Well, if we're going to do it for our relationships, we had better do it for chemistry and how different atoms interact as well. And that's really the study of intermolecular forces and bonding. Okay? So before we can get into the intermolecular forces, notice I'm saying inter, we need to understand our intramolecular attractions. Okay? So intra means within the molecule. If I'm going to say, look at an example of sodium chloride, the intramolecular attraction is the bonds connecting the sodium and the chloride. If I wanted to look at, say, the interactions in methane, which is CH4, the intramolecular interaction is the line represented between our carbon and our hydrogen. And if we wanted to look at, say, the intermolecular forces or intramolecular attraction in water, again, it's our line. So it's looking at that line, which is our bond and our pair of electrons, as we learned from Lewis theory. Okay? In Lewis theory, we're drawing those as a line to represent two electrons. Okay? And there really isn't any difference between that line all the way through this, which would theoretically mean that that line is identical in each of those cases, which means we're calling that bond the exact same in all cases. Okay, well, if that's true, then I would expect the exact same results from each of these compounds. And yet, when I take a look at methane, I see a gas. When I look at water, I see a liquid. When I look at sodium chloride, I see a solid. Okay? Well, if the bonds are all the same, why am I getting different phases? Okay? So, step one, those bonds are not the same. Okay? And you should be able to recognize now what those differences are. In the first case, we have sodium, which happens to be a metal, and our chloride, which happens to be a nonmetal. And when we go through and look at water, our hydrogen and our oxygen, you'll notice they're both nonmetals. And when we look at our methane, carbon and hydrogen, they're also nonmetals. So at a first pass, we can separate the metal-nonmetal, our sodium chloride, out as a separate type of bond. Okay? It's a different bond class because it involves a metal. Okay? We name that ionic. Okay? It's an unequal sharing of electrons. Okay? And it's in fact so unequal that sharing isn't really an appropriate term. They aren't really sharing electrons. They're kind of giving up electrons or stealing electrons from the other. Okay? And we could rank that sharing ability by looking at the difference in electronegativity. Okay, the problem with looking at our difference in electronegativity is that nobody memorized the electronegativities, and we don't want to. Okay? Officially, our difference in electronegativity for an ionic bond must be greater than roughly 1.7. Okay? Well, we came up with a rule of thumb definition that works out really well for us, and that's if we notice a metal bound to a nonmetal. Okay? And we're used to that definition. We've seen it already. Okay? If we move to, say, our water and our methane, this one gets a little bit tricky. Okay? So we're going to have to subdivide this one out. If we look at this, we're looking at nonmetal bound to nonmetal. Okay? The problem with that definition is that we would then expect the exact same results out of both water and methane, and yet we don't get the same results. Okay, so something else is going on here. We need to further sub-categorize those individual sections. Okay, and that's where we come up with this term polar covalent versus officially non-polar covalent. As you might have guessed already this semester, I personally happen to be very lazy and will drop the nonpolar and just call it covalent. I'll try and bring the nonpolar back in. Okay? So how can I tell the difference between these? Okay, well, they're both non-metal bonds, so that's not helpful. What I could do is use the information that I had in the ionic, and the ionic said a difference in electronegativity. Okay? And we also had this sharing rule. So if I go through and look at the nonpolar covalent, what we're looking at here is a perfect, whoops, not prefect, a perfect sharing of electrons. Okay? And our polar covalent is a not quite perfect sharing of electrons. Okay? So it's a little bit less perfect than our nonpolar covalent, but it is nowhere near the unequal not sharing of electrons in our ionic compound. Well, again, that's really, really vague. How do we look at elements or bonds to kind of predict that? Okay, so we need more information. Again, don't tell me nonmetal bound to nonmetal. That's useless as a definition because both polar covalent and nonpolar covalent set us up that way. We could look at our difference in electronegativity. Okay, for the nonpolar covalent, our difference in electronegativity must be less than 0.5, roughly, which then means our polar covalent difference in electronegativity has to be greater than 0.5, but less than 1.7. And again, we don't want to memorize electronegativities, so that's probably not helpful. We need, again, another kind of rule of thumb. The rule of thumb that is going to become very, very, very useful, and you must have this memorized. The nonpolar covalent is anything that has the same atom bound to the same atom. Okay, so if I take, say, fluorine, the most electronegative element on the periodic table, and I bond it to fluorine, well, their electronegativities are the same, so that when I do the difference in them, what do I get? Well, I'd get 0, which is definitely less than 0.5, so that works. Okay, turns out that definition is a little bit too narrow, so we add a definition for our nonpolar covalent. That second definition is carbon to hydrogen. Okay, is classified as a nonpolar covalent bond. That sets us up now with our extremes. We have our definition for our nonpolar covalent, we have a definition for the ionic, okay, which leaves us polar covalent. Okay. Well, what do we do for our polar covalent? The difference in electronegativity, somewhere in between. How do I figure that out? Okay. I would argue that your definition there is everything else. Okay. Meaning, if it's not ionic and it's not nonpolar covalent, it must be polar covalent. So if we looked at water, that's oxygen bound to hydrogen. That's not same to same. Okay. And it's also not carbon to hydrogen. It's also not ionic because there's no metal. So that means polar covalent. That's how we'd kind of work through those definitions. Okay. So let's kind of clear some of this up so you can make sure that you memorize the proper things. We really, 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 really need these rules of thumb when looking at our bonds. Okay? If you have the rules of thumb, you should be okay for doing the rest of these steps. So again, ionic, metal bound to nonmetal, polar covalent covers everything, okay? Everything that's not ionic or nonpolar covalent, and then our nonpolar covalent is the same atom being bound to the same atom and carbon bound to hydrogen. Okay, so we need those. What happens when we now bring those separate molecules close to each other? Okay, so we've got a big smattering of things here, so let's simplify this out a little bit. And let's look at just the sodium chloride. Okay. I want to know what happens when I bring one molecule of sodium chloride near a second molecule. Okay, well, there's really two primary ways that those could interact. Okay, we have method 1 and method 2. Okay, well, which one is going to be the primary one? Okay. Hopefully what you can recognize is that because sodium chloride is an ionic bond, and chloride steals all of the electrons from sodium, chloride becomes negative and sodium becomes positive. Okay, so this is looking at our partial charge notation, which we talked about. That same thing is going to happen with our second molecule. Okay, it shouldn't change. And if we now look at our interactions, in one case, whoops, sorry, drew that top one wrong. In one case, I bring the negative near a positive. Well, if I bring a negative near a positive, what happens to the charge? Well, it should cancel out and it should become neutral. And in the other case, I bring a negative near a negative, I'm actually making it more charged or more negative. Well, charge is an inherently bad thing. And we're looking at or chemistry in general, we're always striving for neutrality, which means the bottom interaction is a horrible interaction. It's making things more charged, which makes it less stable, very, very bad. I would only expect to see the top interaction occurring. Okay. What happens if we then scaled away to, say, another example, say our water example? Same idea, we're now looking at just one of the bonds, and I want to look at H interacting with a second molecule. Which way should it interact? Okay, and because I'm kind of picky about coloring, let's go ahead and color that in appropriately. Okay, well, hopefully you spent a little time answering the quiz question, and you would guess that we have our top interaction being the primary interaction. Okay, why? Well, we go back to our bonds and address what's happening. That's polar because hydrogen is less electronegative than oxygen, so the oxygen carries a negative, the hydrogen carries a positive. Okay, because they aren't formal charges, I would include the deltas to represent that they are partially that charge. Same thing would happen with our second molecule. And if we go through and look at our interactions, hopefully what you see is that we would get a more stable or neutralized structure by bringing positive to the negative in our top interaction, which then again means the bottom one is invalid. Okay? Before we move on to the really hard one, let's now try and separate and come up with some names for this. Okay? Well, let's look at the strength of the interaction. Which interaction should be stronger, the red or the blue interaction? Hopefully, you jumped on the red interaction being a stronger interaction. That's because those are formally charged. We're trying to neutralize those really high charges as best as possible. In the blue one, they're only partially charged. Okay? So they don't really need to interact to neutralize their charge because it's partial. They're smaller charges. That means the red one ends up being very, very strong, and the blue one ends up being weaker. Okay. Well, if they're different in strength, we need to come up with different names for them. And this is where we can now create a name, just like dating or marriage or whatever the other one was, flirting. Okay. This is a really strong interaction between those molecules, okay, in our red case. So we want to come up with a name that suggests that strong interaction. Well, chemists being creative like they are, look and say, well, I have an ionic bond on the left-hand side, and I have an ionic bond on the right-hand side. So I'm going to call this interaction ionic, which is pretty moronic because we're looking at an interaction, not an intra-reaction. This is a very subtle difference here. In one case, we're referencing to two separate molecules looking at kind of a relatively weak interaction versus two atoms that are directly bound to each other. Okay? So we can call the ones within the atom ionic bonds, and the one between the molecules ionic forces, to represent that they're looking at different systems. Ionic can still be confusing, so we could go through and come up with a different name altogether. So to minimize the confusion, you can sometimes hear it referred to as electrostatic. We'll use this same idea with our water molecule. Okay? We could go through and say, well, one is polar covalent and the other one is polar covalent. So we could call it a polar covalent force. Okay? We screwed up calling ionic forces ionic. We need a better name so that we don't get confused with it. Okay? So what does polar really mean? Well, polar means that I have these kind of partial charges at opposite ends of a pole. Okay, well, if I'm looking at a pole, there's really just two ends. So really what I have is a two-ended pole, which doesn't sound very scientific until I turn that 2 into a Greek prefix, and I end up with dipole. What happens with the other one? Well, that one was a dipole as well. What kind of force is now between those two dipoles? Again, really creative here. We have a dipole-dipole force. Okay? And we've now come up with 2 of our arguably 3 intermolecular forces. Okay? The last intermolecular force, unique intermolecular force, would be the trickiest one to look at. Okay? And this is one that we'll have some quiz questions on and we'll discuss in class next week as well. Which interaction should win out, the top or the bottom? That is a very challenging question. Okay? So I'll give you some other hints to go along with this. That interaction happens to be the weakest interaction. Okay? It is so weak, in fact, that we tend to ignore its effect. Okay? Or at least we ignored it until a very smart person came along and said, actually you can't ignore that, that's actually kind of an important force. It does contribute to our overall structure. That person happened to be called van der Waal. Because he went through and said, no, you all are wrong, he then gets his name associated with that force. So we can refer to it as van der Waals forces. I'm not a big fan of naming things after people's names. Okay? And apparently somebody else had the same opinion and referred to it as a London dispersion force. Okay? And we'll look at some images again on Monday or Tuesday to help explain that. Okay? The last one that you might see reference to is something known as an induced dipole, which I don't want to write out again, much the same way as that we look at our dipole-dipole force. Okay? That one takes way too many letters. I'm way too lazy for that. Okay? Don't even want to bring that really into the picture. Okay? I'm actually so lazy that I will refer to our weakest force actually as our LDF, for London dispersion force. Okay, so those are our 3 primary categories for our forces, and we now have different names for them as well. So what we need to know is what are those forces, okay, and their relative strengths and weaknesses, okay, and which molecules generate these forces. Okay? But as we just went through, if you know what your molecule or your bonds are, you should then be able to predict the type of force coming out of it. Okay? That was the whole point of this slide. So, to summarize our forces, our ionic or electrostatic forces are coming from ionic or electrostatic bonds. Okay? So we can call it sourced. Okay? Our dipole-dipole force, again with that whole color coding, is sourced from polar covalent bonds. Okay, so if we can identify our polar covalent bonds, we can see dipole-dipole forces. And our last one, our London dispersion forces, is sourced from our non-polar covalent bonds. I keep leaving that N off. Okay. And you might be saying, well, Mike, you clearly can't count because there was a 4th one listed there called hydrogen bonding. Well, hydrogen bonding is not a unique force. It is a dipole-dipole force. It gets its own special name because in addition to it being a dipole-dipole force, it happens to be a really, really, really strong dipole-dipole force because we are combining 2 atoms in a polar covalent bond that happen to have drastically different electronegativities, i.e. hydrogen being bound to fluorine, most electronegative element, hence really big differences. Oxygen, second most electronegative element, big difference. or nitrogen, third most electronegative element. Okay? If we have a dipole-dipole force and we have a hydrogen bound to fluorine, oxygen, and nitrogen, then we have hydrogen bonding. Okay? So we have to follow all of these kind of steps to kind of move our way up. That's how we get through. So we now have ways to identify the intermolecular attractions. And again, you might be saying, well, why does this matter? Okay, well, it matters because of phase transitions, melting points, boiling points. Guess what we can do with these forces? We can predict relative boiling points and melting points. Vapor pressure. We can predict how much vapor pressure to expect, a lot or a little. We can look at something about viscosity. We can look at surface tension. We can look at solubility. We can even look at the potential for doing a chemical reaction based off of these intra and intermolecular forces. Okay? So being able to look at a structure and say, these are the bonds and forces that are at play, allows a myriad of possible options for qualitative observations. Okay? So as you might guess, I'm a very qualitative person, not quantitative, and that's why I really like our intermolecular forces, because it can get me a lot of information without having to do anything involving a calculation. Okay? So it becomes super, super important. Okay? The last thing I want to address is that figure to the left. This summarizes all of the bonds and all of the forces in kind of a neat wheel, though it didn't provide any definitions within it. And because I wanted to get this under 30 minutes, I won't go into it a whole lot of detail, but if we look at a compound, okay, say, or a bond between, say, carbon and hydrogen, okay, well, what we would then do is classify that according to our ionic, polar covalent, or covalent. Okay. Carbon and hydrogen technically has a little bit of polarity, so it is probably this kind of dark purple-black color of a covalent bond. Okay. The beauty of this chart is that if I want to then determine its force, I then only need to match that location in the force section. Okay, well, in the force section, that is in the London dispersion section of our forces, which would mean the type of force I would expect for a carbon-hydrogen bond is a London dispersion force. Okay? What if I change the bond type? Instead of being carbon to hydrogen, I became sodium to chloride. Well, that is now an ionic bond, metal and a nonmetal, fitting most classically up as an ionic bond. That is going to correspond to the matching color in our force wheel. Okay? So it's kind of a neat little comparison. If I say had a yellow bond, which I can't highlight in here, but if I had a yellow bond, that's going to correspond to a yellow force. And I'm now classifying each of those individual categories according to what color you will within the color wheel, which is really coming back to electronegativities. Okay? So again, we'll revisit this diagram on our next lecture. Okay? But the last thing I want to leave you with would then be trying to apply this. So what I want you to do is predict which compound has the higher melting point within these four questions, either compound A or compound B, and come up with an explanation for this. For the sake of this assignment, I want you to do a couple things. Number one, take a hot minute here and determine the definition for a melting point. If you can't write it down, then look it up. And two, what I want you to go through and do is decide which compound has the higher melting point or boiling point, and number 4. Okay? I know it's a bit weird to jump to 4 instead of 1, but I would argue 1 is probably one of the hardest ones on here. 4 is one of the easiest ones to go through and approach. Okay? And with that, you should be done with your video lecture for Thanksgiving. So enjoy your turkeys, or at least enjoy the break, whatever bit of it you can get. Hopefully you do a little bit of chemistry review, and we'll see you bright and early Tuesday morning.